Okay, so why don't we start? But before we start, does anybody have any questions? Okay, so last time we talked about Rolle's theorem and the mean value theorem. So let's do this example here, and it might involve one of the two. So suppose that you have a function whose derivative is greater than or equal to 3 and also less than or equal to 5 for every single x. And the goal is to show that f of 8 minus f of 2 is always in between 18 and 30. Okay, so can someone tell me what theorem you think can be used here? What do you think? So let's kind of review maybe what the theorems we did last time. Oh, I think someone has their mic on, so just make sure you're muted until you have a question. So Rolle's theorem, which one was that? Was that if you have a continuous function on a closed interval that is differentiable on the open interval, and also if you had f of a is equal to f of b, what does that mean? There is a c in between a and b where the derivative is 0. So that's what we did last time. So mean value theorem was the same setup for Rolle's theorem. We also have a continuous and differentiable function. However, it's a bit more general, right? We didn't require that the endpoints be the same, but the c that exists for mean value theorem is that the derivative is equal to the slope of the secant line. So one way we talked about this was there is a tangent line parallel to the secant line. So let's look at this question here. Which of the two do you think applies to the question? Anybody? Let me give a guess. Well, mic check. Can people hear me? Okay. All right. So, any guesses which theorem you can use? So last time we did something at the end of class. Yeah, we did used a mean value theorem. Well, we had something with inequalities, right? The last what we ended with last time. So yeah, it is mean value theorem, and the main way to see that, a couple things maybe should jump out at you. Well, first of all, the derivative is never 0, right? So maybe Rolle's theorem may not make sense. You also have a difference of two functions, right? And then we also have a difference of two functions in the mean value theorem. Yeah, so let's try that. Let's think about the interval 2 to 8. What do you know about the interval 2 to 8? Use the mean value theorem. So what do you know about f of 8 minus f of 2 over 8 minus 2? So this is the secant line, right, between x equals 2 and x equals 8 for the slope of the secant line? What do you know about this value? Well, let's look at the mean value theorem, right? Here was the slope of the secant line, f of b minus f of a over b minus a. And this is equal to some derivative inside 2 comma 8. So for some c, where 2 is between c and 8. Okay, so just tell me, what do you know about f prime of c? What value must f prime of c be, or in between? Let's read the supposition. Not 18 and 30, that's what we want to show. Right, that's gonna, so using this, we're gonna do something with this. Not 2 and 8, right? 2 and 8 are the intervals. But read f prime, right? F prime is a derivative, right, of f. And we know that derivatives of f, of this f, are in between 3 and 5. So what does this mean is that whatever f prime of c is, we know it's equal to f of 8 minus f of 2 over 8 minus 2. And we also know it's in between 3 and 5. So does everyone see that? So these numbers come from f prime. So once you write this, then the rest is not that bad, right? All you do is multiply by 6 everywhere, and then you get 18 f of 8 minus f of 2, and then 30. Right? Yeah, so once you write out the mean value theorem statement, then yeah, just make sure you know where you place the inequalities and what values. Then you just solve for the thing you want, f of 8 minus f of 2. Okay, so any questions on that? So just an example of a question that about the mean value theorem. Okay, so continuing on for what we're going to do today, the main things we're going to be looking at are really how the derivative gives information about the graph. All right, so some of the tools that we're going to be doing today is we're going to use the derivative to determine where f is increasing or decreasing. We're going to see where f is has a local max or min. So we already kind of know how to do that right now. We're going to determine the concavity. We've talked about concavity a little bit, but we'll give a better definition of it today. And then we're going to talk about something called inflection points. So again, that will be that'll make sense later. So the two main tests we're going to use are something called the first derivative test and the second derivative test. Okay. Okay, so why don't we start with what does it mean for a function to be increasing and decreasing? So we have kind of talked about that, but let's give it a little math definition. So we'll say that f of x is increasing on an interval AB open if for all x values, say x1, x2, where well, let's say x1 is less than x2. So if I look at a smaller x value and a bigger x value, what does that mean about the y values? The y values are also going to be increasing. So in other words, as x increases, y increases. So decreasing, it's the obvious statement that as x increases, the y's decrease. As x increases, y decreases. Okay, so do you have any questions just in that definition? Why does that, make sense for increasing or decreasing? So let's just kind of like sketch. So here's an interval AB, and here's a graph. So if you pick any two x values in between, here's x1 and here's x2, then if you compare the y values, so an alternate so this is for increase. An alternate definition is to say that f of b minus f of a is greater than 0. Right? That would imply that f of b is greater than f of a. So similar for decreasing. If you pick any two x values, and compare their y values, oh, not f of, that is also true, but f of x1, x2. Sorry. Let's say this is f of x2, that's f of x1. If you compare their y values, x2 is going to be smaller in this case. In other words, their difference will be negative if you always choose x2 first. Okay, so just questions on that kind of basic statement? Definition of increasing and decreasing? Okay, so what are we going to do with this? Is that we're going to say something about the derivative. Okay, so let's say if you know that the derivative is always positive on an interval, let's say AB. Okay, you tell me, what do you think based on what you know about derivatives? Do you think the function is going to be increasing or decreasing? Yes, it is increasing. So this kind of is maybe clear based on like the picture. If you have positive tangent lines of some curve, let's say if we know the tangent lines to begin with, then if you kind of like fill in the blanks, then you can see it's increasing. But to prove it kind of rigorously, maybe there's some weird example that we don't know of. Let's just try to see how the proof would go. Okay, so what we're going to do is use the mean value theorem. So notice that in our first question today, the mean value theorem is pretty helpful when you know about or want to find out, or when you know about bounds of the derivative. So if you know, so in our example, we had the derivatives of in between 3 and 5. So the bound that we have in our derivative here is that the derivative is always positive, right? It never dips below 0. So that's kind of why mean value theorem might make sense here. Okay, so this is what we're going to do, is we're going to choose any interval inside. Okay, so let's do that. So I'm going to call it, let's call it D and E. I'm not going to use C because we're going to use that later. We're going to call it DE. Okay, what do you know about, if you were to draw a line in between D and E, what do you know about the slope of that line? So this is using the mean value theorem. So first of all, what is the slope of that line? Can someone tell me what the slope of that line is? Good, yeah. That is the secant line, slope of the secant line. So we have f of E minus f of D over E minus D. And what do you know about that value? So now we use the mean value theorem. What do you know about that value? That must equal something, right? What does the mean value theorem say? So the slope of that line is equal to what? Good, yeah, there is a tangent line that's parallel. So if we draw a picture, that means there's some value in this little interval. Maybe it's here, where the tangent line is parallel. So it's precisely inside, so let's call that value C. So we know what is the slope of the tangent line. It's precisely the derivative. Okay, so let's do it. Let's see what this gives us. Let's just multiply by E minus D on both sides. Okay, so tell me, if this function is increasing, what should the value of E minus D be? Should it be positive or negative? It should be positive, right? We want this to be positive, right? Because E is further to the right. What is the what is e minus d? Is that positive or negative? Yes, that is positive, because e is to the right. And what is f prime of c? Is that positive or negative? Positive, right? That was the supposition. All right, so is f of e minus f of d positive? It is, right? Yeah. Any two positive numbers, when you multiply them, always gives you a positive number. So f is increasing. On dE. So, um, so you can choose any interval inside. So f is increasing. Sorry, f inside AB. So dE was arbitrary, right? So since it was true for some arbitrary interval inside, it's true for everyone. Since true, since true for any interval inside AB, f is increasing on AB. Okay, so I'm not going to do the proof for negative because it'll just be mirrored, but if f prime of x is negative on an interval, then it pretty much mirrors out, but you might have this term would be negative, right? Then f is decreasing on 8. Okay, so any questions about that? So we have a direct relationship between increasing and decreasing. By the way, is the converse true? If f of x is increasing on an interval, is f prime positive? What do you think? Um, so it's not going to be negative, right? If it were negative, then f would be decreasing. But is that like, do they go hand in hand? Sorry, yeah. If you have a function that's increasing on an interval, any function, is it necessarily true that the derivative is positive there? No, yeah. Um, yeah, where do you think it could not be positive? What's an example? There's a couple examples. One example is x squared, or cubed, right? The derivative is x squared, which is equal to 0 at 0. Right? So you have the derivative equal to 0, but it is still strictly increasing everywhere, right? If you choose any two x values, the difference in y values will always be positive. Another example is cube root. So what is the derivative of cube root? Let's see, it's 1/3 x to the 1 minus 1/3. So 1/3, so 1/3 then cube root of x squared. So first of all, cube root of x kind of has this shape. Right? Cube root of x is continuous everywhere, right? Everything makes sense for cube root. Is that true? Like negatives are okay for cube root. But where is the derivative weird? Where does the derivative not make sense? At 0, yeah. At 0, undefined. However, this is still positive. This is still an increasing function everywhere, right? So just nice to, whenever we have these theorems, it's kind of helpful to, like, if you flip the statement, right? This is the flip converse. It kind of helps you kind of understand the statement a bit more and really what the derivative means. So the derivative is not directly related to increasing or decreasing, but it's correlated. Okay, so let's do an example. Find where f is increasing or decreasing. Okay, we have f of x is equal to x cubed over 3 plus x squared plus x plus 1. Okay, so we're all masters at derivatives now. So what's f prime? Good, yeah, x squared, because the 3 and the 3 cancel, plus 2x plus 1. Okay, so we need to find where f prime is positive and where f prime is negative. Can someone put this into a form where it's easier to see when f prime is positive and when f prime is negative? What can you do to this? How do you find out? First of all, can you factor? Oh, good, yeah, factor, got it. What does this factor out to be? Yes, x plus 1, x plus 1. And to be more clear, x plus 1 squared. So the squared part should tell you something. Is f prime ever decreasing? Where we know when f prime is negative, it's decreasing. But this is always positive, or 0. Except, where is it 0? value makes it 0? -1, yeah. Okay, yeah. Um, so it's increasing everywhere. Okay, so let's do another one. It's a bit more interesting. Let's do x cubed over 3 plus 3x squared plus 5x plus 6. So the goal is increasing and decreasing. Find where it's increasing and decreasing. Okay, so what's the derivative? Good. X squared plus 6x plus 5. Okay, how do you factor this? Good, x plus 1, x plus 5. Okay. All right, so this is kind of a statement that will kind of help us with future rules. So this is a thing you maybe should know already, but a function only changes sign where it is A, not continuous, or B, an x-intercept. And I should say only possibly changes sign. Can someone tell me why this is true? Good, yeah. This is a consequence of intermediate value theorem. Yeah, so intermediate value theorem is that if you have something positive and something negative, there has to be an x-intercept in between, right? So if you don't have an x-intercept, you can't change sign. If you do change sign, then you have to be not continuous. Right, this is not continuous. And this is an x-intercept. Okay, another way of saying this is the following. And let me know if you understand why. If on an open interval, f is continuous with no x-intercepts, then if you know a value of c inside f prime of c greater than 0 implies what, you think? If you know the value of one x value inside, and you have and you're continuous with no x-intercepts, what do you think you know about f? So you have, here's an open interval, and we have no x-intercepts. So it's never going to hit the x-axis. Moreover, it's continuous. And what do you know, if f prime of c is bigger than 0, just for one value, f prime of c, that you know, what does it tell you about all of f? Yeah, it has to be all greater than 0. Right. There can't be anything less than 0, because what does that imply? By intermediate value theorem, if there was something less than 0, it would have to cross somewhere at x-intercept. But we suppose that there are no x-intercepts. Okay, so that's kind of a wordy way of saying, how do you determine where f prime is positive or negative? Well, you have to look at the x-intercepts. And then, or not really look at the x-intercepts, but look at everywhere else, all intervals that do not contain x-intercepts. So first you need to find the x-intercepts. So how do you find the x-intercepts here? Or where it's not continuous, or where it isn't continuous, but that's not a problem here. Yeah, so if you set the whole thing equal to 0, and then solve each factor for x, because if the product is 0, then one of the things must be 0. So x plus 1 equals 0, or x plus 5 equals 0. So x equals -1, or x equals -5. Okay, so I'm going to do a new page, but any questions so far? Okay, so I'm just going to rewrite the question. So we had y prime is equal to x plus 1, x minus 5, plus 5. And we had the zeros of the derivative. Is -1, -5. Oh, by the way, I mean x-intercepts of the derivative. Right, of course not the original function, if that wasn't clear. Okay, so we know that the zeros are -1 at 5 and -5, but that means that everywhere else it's not 0. So let's look at a number line. We have -5, smaller, and -1. Now everywhere else it's not 0. Okay, so this little fact here says that if I'm on an open interval that's continuous, which our derivative is continuous, and there's no x-intercepts, that is true, there's no x-intercepts here or here, then all I need to know is one value of c inside the interval, and then I can determine the sign of everything. Okay, so let's start over here. Can someone give me a test value over here? Yeah, 0. Always 0. Oh, and what do you plug in? What do you plug 0 into? Yeah, just for f or for f prime? Good, yeah. So we're plugging into the derivative. Okay, so what happens when you plug in 0? So here's a little trick that I like to do, is that we don't care about, I mean, it's easy for 0, but here's a little trick. We don't care about the actual value. We only care about the sign. Remember, in the beginning, we were trying to find out right, where the derivative is positive and negative determines where the function is increasing or decreasing. So if you factor out a derivative like this, it's very easy to see where it's positive and negative. So if you plug in 0, is the first factor positive or negative? It's positive. And when you plug in 0, the second factor is positive. So positive times positive is positive. Now, I know it's simple for this case, but I assure you it'll be very helpful when you have kind of long strings of factors. You might, since all you care if something positive or negative, it's probably easier to do it some other way, like this. Okay, someone give me a value inside -1 to -5, or -5 to -1. What's a value? -3. Okay, so this is where it's a bit more interesting when doing this trick. When you plug in -3, is the first factor positive or negative? Negative. When you plug in -3, is the second factor positive or negative? Positive. What's positive times negative? Negative. Cool, so we didn't have to actually calculate anything, right? We just had to see if the thing was positive or negative. Okay, how about test value over here? How about, I don't know, -10? Is the first factor positive or negative? You plug in -10. Yeah, negative. And the second factor? It's also negative. What's a negative times negative? Positive. Okay, so I like that method just because you don't need to plug anything in. So what's the answer? Where is it increasing? Or maybe we can do decreasing first, because that's easier. Whatever you want to do. Yes, decreasing between -5 and -1. Yes, it's increasing from -infinity to -5. And so it's a union of the two, -1 to infinity. Yeah, good. So just remember the union when you have two separate or more intervals where it's true. Okay, so everyone see that? It's okay, yeah. Okay, so let's kind of boil it down. So the increasing or decreasing test. find derivative set to 0 or where it doesn't exist. By the way, what are these numbers? Where the derivative is equal to 0 or where the derivative does not exist? What are those numbers called? Critical numbers, yeah. Inflection points are going to be later. Critical numbers. And then use test values in between critical numbers to determine sign. Okay. Okay, so as you imagine, or maybe have been thinking about, this test should be helpful for finding maxes and mins, right? We know when the derivative is 0, or at a critical number, that's where maxes and mins might occur. So we pretty much have done everything to determine if something is a max or min. Let's give a name to it. This is called the first derivative test. Okay, so let's just say it again. Local max and local mins occur at critical points. So we've talked about this when talking about like Fermat's theorem, Rolle's theorem, or extreme value theorem. So how do you know if your critical point is a max or min? So here's the statement. F of C is a max if for close values of f prime to the right, to the left of C, is positive. And for close values to the right of C, f prime is negative. Okay, so let's see that in a picture. Okay, if I have an interval where the derivative is positive, what do you know about the function? If the derivative is positive somewhere, what do you know about the function? Well, just derivative is positive. That isn't not necessarily max, but if the derivative is positive, what does that tell you? It's increasing, yeah. So the general shape of the graph to the left of f of c is increasing. And again, to the right of f of c, f prime of x is negative as a statement. So that means that it's decreasing. So that kind of intuits why it's a max there. Okay, so then similarly, a min, if for close values to the left, f prime of x is negative, and close values to the right is positive. Okay, so picture. If to the left it's negative, it's decreasing. And you have some value here, and then to the right it's increasing. So f of c. Okay, does that make sense? Okay. So if the derivative does not change sign, at at c, what do you think is true about f of c? So if the derivative doesn't change from positive to negative or negative to positive, what do you think f of c is? Yeah, it's neither a max or a min. Can you think of an example? It's an example where that's true. Actually, we gave these examples earlier. Yeah, so it could be on an increasing interval. So for example, y equals x cubed, right? The critical number is at x equals 0, because that's where the derivative is 0. But it's not a max or a min there. And the other example we gave was cube root. It's also critical at 0. Where the derivative is undefined. And it was still neither a max nor a min. Okay. So you have to check both sides to determine if it's a max or a min, not just one side. Okay, questions? All right, we'll take like a 5-minute break, and I'll put up a question for you to think about and stretch. Walk around. All right, let's say find local maxes and mins always, if any, of f of x is equal to x plus 1/2 sine of 2x. And let's say on 0 to 2 pi. Okay, so let's meet back at 6:35, and we'll go over this one. All right, someone tell me what's the first step to find a local max and min? What do you do first? Yes, find the derivative. So notice that like our steps for finding local max and min aren't too different from finding where it's increasing or decreasing. So what is the derivative? It's 1 plus, and here we have 2 over 2 cosine of 2x. It's 1 plus cosine 2x. So that's chain rule here, right? Okay, what's the next step? Yes, so technically we're finding critical numbers, but the only critical numbers we have where the derivative is 0. Okay, so we have 0 is equal to 1 plus cosine 2x. How do you solve 0 equals 1 plus cosine 2x? We did an example similar to this a couple classes ago. How do you deal with cosine 2x? Oh, without using inverse function? But technically you could. Well, actually, you have to be careful when you use inverse function, right? Yeah, can someone tell me why you have to be careful when using inverse function? It's a good point. Why do you need to be careful? That's why I think you should never do it. Using arc cosine or cosine inverse. Can someone tell me? What's something special you know about arc cosine or cosine inverse? What values does it give you? What's the range of cosine inverse? Do you remember which one? Okay, maybe not. That's okay. It's hard to remember. So arc cosine will only give you values in 0 to pi. So if you have a value for cosine, let's say when you did arc cosine, you got this value. I don't know, let's say it's 3 pi over 4. Arc cosine will not give you this value, right? arc cosine does not give this value. So was it like 5 pi over 4? So do you see the danger? I mean, if you know to fill in the blanks after doing that, that's fine. Like, include all the other values. But we can do this without even worrying about that. First of all, does that make sense to everybody? And remember that? Does that ring a bell? That arc cosine doesn't give you all the values you might want. And that's the same for the other trig functions. Arcsine and arctangent may not give you all the trig functions you want, or all the values you want. So again, like both of these values have the same x value, have the same cosine value, so that could be an answer. Okay, so if you don't want to use arc cosine, what do you do? How do you deal with the cosine of 2x? You could do that, but for practice, can we do a different way by factoring? Or yeah. So if you had nothing to set it equal to, how would you like factor 1 plus cosine 2x? Like if I had y equals 1 plus cosine 2x, how could you factor that? Yeah, double angle formula. So you have 0 is equal to 1 plus cosine squared minus sine squared. So you probably want to turn one of these things into the other thing, right? So why don't we turn cosine squared into 1 minus sine squared? Then we have 0 is equal to 2 minus 2 sine squared. Okay, so how do you factor this? First of all, we can bring a 2 outside. How do you factor 1 minus sine squared? Anyone know? What does that look like? Good, yeah, that's a difference of 2 squares. 0 is equal to 2, 1 plus sign, and 1 minus sign. Okay, so why was I not letting you bring things to the other side? Is because this is f prime, right? We didn't need to set anything equal to 0 yet, right? So this is f prime factored. So when you factor something, it's going to be very nice and easy to use the derivative test. And I'll show you a way that if you did it a different way, you might get something, that's tricky. Oh, can you do... yeah, but it would be 1 equals sine squared plus cosine squared, right? Good, okay, yeah. Yes, you could do that. So that would, so this would be cosine squared plus sine squared. Yeah, then you would get 2 cosine squared. That's fine, yeah. That's actually probably maybe easier. Yeah, good. But anyway, so we got here. Okay, so now if I set this equal to, so notice that this is the derivative, right? This was just a refactorization of 1 plus cosine 2x. So now if we set this equal to 0, we can easily determine where this thing is equal to 0. Okay, so that's where 1 plus sine of x is equal to 0, and 1 minus sine of x is equal to 0. Okay, so where are those places? Where is sine equal to -1, and where is sine equal to 1? Remember, this is on 0 to 2 pi. Good, yeah, so the pi over 2 is the 1, and the 3 pi over 2 is the negative. Okay, so we're trying to find local maxes and mins. So what do you think we should do next? So those are critical numbers, right? These are critical numbers. So what do we do next? What do we do to use those critical numbers? Good, yeah, check the close left and right values. So I'm going to do a new page. We have f prime is equal to 2, 1 minus sine, 1 plus sine. We have the critical numbers of pi over 2 and 3 pi over 2. And we're checking close left and right values. So pi over 2, 3 pi over 2, and then we stop at 2 pi. Okay, so this is where the derivative is 0. And we want to check what the sign of the derivative is in between. So someone give me an in-between value between 0 and pi over 2. Or someone tell me why we don't need a specific value. What do you know about sine when you're in between 0 and pi over 2? What do you know? What is this, first of all? In terms of quadrants, what is this? Yeah, this is quadrant 1. What do you know about sine in quadrant 1? Positive, yeah. What else do you know about, so looking at the derivative, what else do you know about sine that you probably would want to say? Like, let's just look at this example. If sine is positive, is 1 minus sine ever negative? No, yeah, why is that true again? Good, yeah. So if you know that sine is positive in the first quadrant and that sine is always less than or equal to 1, well, we don't need the equal part because that's pi over 2, because we're not really considering pi over 2. Then you can do the little plus minus trick. So we can ignore 2 because 2 is always going to be positive. So 1 minus sine is always going to be positive, and 1 plus sine is always going to be positive. So it's positive here. Okay, so what is this quadrant or quadrants? What's going on between pi over 2 and 3 pi over 2? Yeah, this is 2 and 3. So sine is different in these quadrants, right? So maybe it's best just to pick one. Pick a number that's good. What's a good number to plug in? What's the easiest number you can think of? It's a very nice value for sine in those quadrants. Good, yeah. Plug in pi. F prime of pi. So it's 0, right? So that means it's positive, because 1 minus 0 is 0, and then it's positive. So this is positive. Okay, so let's go on to this one. What quadrant's this? Well, it's only one other that's left, quadrant 4. And what do you know about sine in this quadrant? It's negative. And is there a maximum to what sine, or minimum to what sine can be? Yeah, it's always going to be bigger than negative 1. Okay, so let's think about these. So 1 minus something negative is always going to be positive, right? The minus minus cancels. This is positive. Now, what about 1 plus sine? Is that positive or negative? Positive, yeah, because since sine is never bigger than or smaller than negative 1, this third term will never be negative. Huh, okay. So where are maxes and mins? Do they exist? We have the derivative is positive, positive, positive. So what do you think that says about maxes and mins? Good, yeah, there aren't any. There are no maxes. Local maxes, right? We know that we could find an absolute max, or min, which I bet you the min would be 0 and the max would be 2 pi. But there are no local maxes or mins. And just say why is that true? Why is it true? What about getting all positive tells you there's no max or mins? Okay, so this was our third statement. There's no change in sign. There's no change in sign of the derivative. Okay, so if you're curious, what does this function even look like? Kind of looks something like this. It flattens out some places. That's where the derivative is 0. And it's always increasing. So it never dips down. Okay, any questions on that? Okay, so again, first derivative test, is pretty much the same as the increasing test, but you're kind of analyzing from there. Okay, so let's talk about the second derivative. It's usually the more interesting one, or just peculiar one. Okay, so when we first started talking about concavity, when talking about like sketching the derivative, um, it was kind of a wishy-washy definition, right? If it's shaped down, it's concave down, right? If it's a frowny face, it's concave down. If it's concave up, it's shaped like this, like a happy face gets concave up. That's not really a nice definition, but we can be a little better with our definition, both by using the second derivative and tangent lines. Okay, so look at concave down and then see if my statement makes sense. A function is concave down. So this is a definition. If all tangent lines, say concave down on an interval, right? It may not always be concave down, might switch. Is concave down on an interval. If all tangent lines lie above the curve. Okay, so let's take our favorite concave down function and try to draw any tangent line. No matter what tangent line you draw, it will always lie above the curve. So it's always going to be above. It's always going to be above. It's above. Everyone see that? Every tangent line you draw is always going to be above the curve. Okay, so what does above the curve mean? One way to say this is that if L of x is the tangent line, is any tangent line, then what do you think the evaluation of, let's actually do f of x minus L of x. Is this positive or negative? So you take f of x and you compare it with L of x. Is this positive or negative? Or it could be 0 if you pick the right point, but negative. Yeah. Yeah, so, and why? It's because L of x is above and f of x is below. So the difference will be negative. Okay, so similarly, it's concave up if tangent lines are under the curve. So that's like this. Every tangent line you draw is always going to be underneath the curve. It's a bit more mathy of a definition than, happy face, frowny face. So what does he mean by f of x minus L of x? Positive or negative? Be positive. Yeah, so F is always going to be above, and L is always below. So there's, when you take the difference, it's always going to be positive. All right, so any questions on that definition? Does that make sense as a definition? So now we know how to find concavity just by drawing tangent lines. Now it can get a little weird around some points about determining if the tangent line is above or below, but that's a way of defining it using tangent lines. Okay, so the goal today is, or for the rest of class, is going to be talking about how the second derivative plays a role in concavity. So this is going to be similar to our proof of the first derivative test. This is called second derivative test. I'm going to use it for concave down. If the second derivative is less than 0 on an interval AB, so then the claim is F is concave down in AB. So this is just analogous to our first derivative test, right? We had, if the first derivative is negative on an interval, then the function is decreasing. So the second derivative component is, if the second derivative is decreasing is negative on an interval, then F is concave down. First of all, using the first derivative test, what do you know about the first derivative on this interval? So if you know the second derivative is negative on an interval, what do you know about the first derivative? So it's kind of funky. So if the question is confusing, let G equal F prime and G prime equal F double prime. Like, so if G prime of X is less than 0, then G of X is what? It's decreasing, yeah. So if we know something about the second derivative being positive or negative, well, since the second derivative is just the derivative of the derivative, that just tells you the derivative is decreasing. Okay, so we're going to use that fact in the proof. Okay, so how do you know if it's concave down? You want the f of x minus L of x to be negative, right? This is what we want. Okay, so what is L of x? What is the tangent line at some point? Let's say that at the point is D and then f of D. What's the tangent line? So if you want to do step by step, if we know the point, what's the other information we need? Good, yeah. We need the slope, so that's the point, and the slope is f prime of D. So L of x minus f of D, but we can put this the other side, so f of D plus f prime of D, so this is point slope form, x minus Okay, so we want that, so we can say f of x is less than L of x. So we want f of x to be less than this. Right, the right hand side is L of x, and the left hand side is f of x. Okay, so let's do it. Okay, let's just see this as a picture. Here's my concave, or perhaps concave down function. This is where the derivative is, second derivative is all negative. And we have this point D. Okay, so we're going to look at all values to the right of D. Look at any interval starting at D to the right. So when I say any interval, I just mean D comma x. So it's arbitrary. So it could be over here, it could be over here, it could be over here. So our statement is going to be true for every single x we choose. Okay, what if I draw a line between D and some point x? What do you know about the slope of that line? What statement can you make? What theorem can you say about something about the slope of that line? Yes, mean value theorem. So the slope of that line is f of x minus f of d over x minus d. And this is equal to some f prime of c in between. So somewhere over here, it's in between. But very importantly is that c is bigger than d. Right, because we're looking at something to the right. And c is inside the open interval dx. Okay, so let's change this up to make it look similar to something we might want. F of x minus, or equals, f of d plus f prime of c x minus d. Okay, so let's compare everything we have. We have f of d plus f prime of c x minus d. This is equal to f of x. And then what was our L of x? It was f of d plus f prime of d x minus d. This was our L of x. Okay, question, which one's bigger? F of x or L of x? Well, there's not much difference between the two things, right? What's the only difference between these two expressions? Right. Only difference is f prime of c versus f prime of d. Which one's bigger? And how do you know? What haven't we used yet that I said we probably need to use? Yes, why is f of prime of d bigger? Yes, because the second derivative is negative, and that implies that the derivative is decreasing. Right, since c is bigger than d, f prime of c is bigger than f prime of d because c is bigger than d. And f prime is decreasing. So that's it. So we know that this value is less, so f of x is less than L of x. Okay, so the next thing you do is look at the other side. So we just looked at to the right side of D. So I won't do the left side, but it mirrors, just you might have some more negatives to deal with. So, but if you're curious, try to figure it out. But it mirrors the proof, but there are some negative things you have to worry about. But that's it. So if the second derivative is negative, then the function is concave down, because we showed that the function is less than the tangent line at some point. Okay, so questions about. So we'll do an example of the second derivative test. But any questions about it? Okay. All right, so let's do an example. Oh yeah. Here's kind of the kicker of the second derivative test. Okay, so if a function, if a let's see, if c is a critical number, and f double prime of c is less than 0. First of all, if the second derivative is less than 0, is it concave up or concave down? Let's just remind ourselves. If the second derivative is negative, is it concave up or concave down? It matches the sign, right? Down, negative, concave down. Then what do you think f of c is? Do you think it's a max or a min? I'm sorry, it's I don't want critical number, because that may not be true. F prime of c is equal to 0. Max, yeah. Yeah, so don't be confused, the less than and down max, right? I would draw the picture. This is concave down, so that picture shows you max. Similarly, if the derivative is 0 and the second derivative is bigger than 0, then f of c is a min. So bigger than 0 is concave up, and then you have a min. Okay, and then one definition left. So if the second derivative changes sign at a point and is continuous, then the point is called an inflection point. So that's the inflection point. It's where the second derivative changes sign. Okay, so let's do an example, and we'll kind of use all these tests with our primary focus on the second derivative test. Let's have x to the fourth minus 2x squared plus 3. So let's find a local max and min using second derivative. And while we're at it, let's find concavity and any inflection points. Okay, so what do you think the first step is? Yeah, we need to get the second derivative. We need to take a little pit stop at the first derivative, right? Because we want to find where the first derivative is equal to 0. So let's stop at the first derivative, and then let's set this thing equal to 0. But first of all, can we factor this before setting it equal to 0? Oh yeah, so yeah, the big thing about an inflection point is that it needs to change sign. So f double prime equals 0 is not enough. Also, the second derivative, yeah. Okay, yeah, so I saw 4x there. So 4x, and then x squared minus 1. Oops. Oh, you're factoring the first one? Well, it's good factoring of quartics. Yeah, so the next step would be to this one, 4x, x plus 1, x minus 1. So I think it's always good to factor first before setting equal to 0, just because using the first derivative test will not be as bad. But we're not doing that here. Okay, so where is f equal to 0? Or f prime, sorry. See, when it's factored like this, it's you can just do it by sight, right? Yeah, 0, -1, 1. Okay, so the second derivative test says all we need to do is find the second derivative. So maybe I look at this and I say, oh, I kind of don't want to deal with plugging numbers into that, though there might be a little trick to, our tricks maybe a little easier, but second derivative is actually not too bad. What's second derivative? Yeah, 12x squared. Squared, remember, because and then minus 4. Okay, so maxes and mins are just plug in 0, -1, and 1. So what happens when you plug in 0? You get a negative number. What happens when you plug in -1? You get a positive number. What happens when you plug in 1? You get a positive number. So depending on the function, like the second derivative might be kind of complicated. You might not want to use a second derivative. So it depends on the function. Sometimes it's easier to find the second derivative and just plug in, or the first derivative test is fine. Okay, so what does this mean? What are these maxes and mins? Sorry, f double prime. Okay, if f double prime of 0 is negative, what does that tell you about 0? X equals 0 is, well, is a max, yeah. So f of 0 is a max. And then these ones are mins, right? Okay, what is the max? Just plug it into the original, right? So f of 0 is equal to 3. F of 1 is equal to 1 minus 2 plus 3 is equal to, what is that, 2? And f of -1 is equal to the same thing, right? Is equal to 2. Okay. So any questions on this? Oh yeah, we have to do inflection points as well. Okay, so how do you find the inflection point, or plural points? And then we'll call it a day. So inflection point is where the second derivative changes sign. So what do you do with the second derivative for inflection point? Well, I think you should set it equal to 0, right? Because a continuous function changes sign. You have to be at the roots. So 0 is equal to 12x squared minus 4. So 4 is equal to 12x squared. And then 1/3 is equal to x squared. So what's x? What's x? Just gotta remember the plus or minus. It's plus or minus radical 1/3. Negative radical 1/3 and then positive radical 1/3. Okay, what are some test values? What's an easy one? Sure, -1. It's fine. Yeah, -1, 0, and 1. Sure. Okay, so when you plug in -1 and 1, you get positive numbers, right? When you plug in 0, you get negative. Okay, so that means these are inflection points. Because it changes sign. From positive to negative and negative to positive. Okay, so we could even sketch the graph at this point. It's yeah, so it's a um, positive concavity over here, and then it kind of switches to negative concavity, and then it switches to positive concavity. It's kind of the general shape. So these points where it switches from positive to negative concavity and negative to positive, that's where the uh, root negative root 1/3, and this is root 1/3. So it's kind of, where the tangent lines are negative, and then suddenly they're positive, or above the graph. Above the graph, below the graph. Okay, so that's all we have for today. So I will see you Tuesday, and hopefully have your quizzes looked at then. But yeah, have a good one. Have a good weekend. All right.